Python Review, Python Fundamentals. We will be reviewing Python 3 in this unit. We will also be referencing Praxis code often throughout the course as we review Python 3. Praxis code is code that is used on the computer science Praxis exam, so you will not see Python. Praxis code has elements of Python as well as unique characteristics that make it its own. Although we will review Python in this unit, and any future units that involve programming, please note that only Praxis code will be used on the Computer Science Praxis exam. Computers are comprised of a very large number of switches, which are either open or closed. These switches were once vacuum tubes, but have evolved over time into integrated circuits. While they've changed tremendously from their early years, they still serve the same purpose. The position of each switch is interpreted as being a 0 or a 1. Machine languages are written in zeros and ones and are the only languages which a computer can actually understand. Another name for machine language is object code. This made programming very difficult for humans. All programmers needed to know, understand, and write machine code. Punch cards were used with holes that represented zeros and ones. They needed to be manually inserted into a reader to execute the program. If the machine did not execute the program correctly, it meant that there was an error in the code. These errors had to be found manually by reviewing the punch cards one by one. Not only was this a difficult skill to master, but finding and correcting errors was a tedious and arduous task. The first programming languages, as we know them, began appearing after the compiler was invented in 1952 by Grace Hopper. A compiler acts like a translator between the programmer and the computer. It takes a higher level language, like COBOL in Hopper's case, which is easier for humans to understand, and converts it to machine language, which a computer can execute. A higher level language, such as COBOL, can be referred to by another name of source code. Source code is the code written by programmers, and is much more easily understood to humans than object code. COBOL paved the way for new ways of programming, such as Fortran in 1957. Fortran was the first of the third-generation programming languages that utilized actual English words and syntax. Programs would be written in Fortran using English characters, then manually sent to a compiler that converted the code into machine language, which could then be sent into the computer to execute the program. The compiler not only converted programming languages into machine code, but also, and more importantly, it debugged programs. Debugging is a critical reality of programming, since errors, or bugs, are an inevitable feature of writing code. Finding and fixing those bugs is an integral aspect of coding. The compiler greatly decreased the amount of time programmers spent debugging by detecting errors and letting them know on which line of code they occurred. Today, a compiler is built into almost all integrated development environments, or IDEs. With this, we are able to write code, compile it, and execute it, all within the same environment. Essentially, we do not worry about compilers anymore because they're always there. The program will not run or execute until it passes successfully through the compiler. With an integrated development environment, programmers can write programs and large-scale software with the assistance of a compiler. A compiler will assist the programmer in locating syntax errors, or errors in writing the code in the correct and necessary style and format. An IDE will execute programs once it is finished compiling. IDEs are incredibly useful to programmers as they provide an all-in-one location to work on and test a program. Although IDEs are powerful pieces of software that have many capabilities, there are many programmers who prefer the ease of programming in an editor. An editor is another type of software that can be used to develop software. Most times, editors do not include compilers, which may make many who are new to programming hesitant to use them. There are many users who prefer working in an editor over an IDE because it has a consistent workflow if multiple languages are being used to program. The methods of using the editor are consistent no matter the language being written, and editors are much more cost-effective than purchasing an integrated development environment. Even with the invention of the compiler, programming in the third-generation languages was not easy. In the 1970s, two researchers at Bell Labs created the C language, from which many of the languages we use today, including Python, are derived. Also, about that time, object-oriented programming, which we will learn about, made it easier for teams of programmers to collaborate on large, complicated projects. Programming languages as we've known them have evolved over time. Here's an illustration of the levels of abstraction for programming languages. High-level languages, up here at the top, are the easiest for humans to understand, as they're the most similar to our spoken and written languages. Now that you've seen some of the benefits and a little history of coding, let's get started. We'll begin by reviewing what some lines of code mean and do, and others, like the ones below, will appear at the start of every program, but we will take on faith that they need to be there without knowing exactly why just yet. So here we have class test : we have the keyword class, which is used to state that we're working within a class, the name of the class, and then a colon ends the class header. Eventually, as we go deeper into this review course, you will understand what each line in the code above does and why it has to be there. The only part that will change for now is what's inside the class in red. Python is a white space dependent language, meaning the number of spaces used must be exact in order for the program to compile and execute correctly. At the beginning of each new statement, there must be 2 spaces preceding the code. So here you see 2 spaces before this first line of code, then you go to the next line, 2 spaces, and then the next line of code. In Praxis code, all code is written in classes or procedures. A class would look something like the Praxis code below. Class, class name, then we have the body of the program here, and then end class, class name. In Praxis code, when creating a class, we surround all of the code included within the class with the class name and this end statement. No other symbols are needed, so you can see there's no colon here, and that's okay because this is Praxis code. We will be writing all of our Praxis code within this structure for now, but we'll expand on all parts of a class and procedure as we review. For now, we'll use the main procedure and include all of our code within it. Like classes, procedures such as the main procedure we'll be using require an end statement. So inside of our class name, we have a procedure, void main, then we have our code in here, and then end main, and then end the class name. Comments are helpful in many ways, allowing a programmer and those who do not know how to program an easy way in which to interpret code. Comments provide a description of what is occurring in a piece of code. In Python, comments start with a pound sign, also known as a hashtag symbol. Comments help programmers by giving them a quick understanding of the program without having to spend time decoding the Python code. They're also helpful for people unfamiliar with Python who would otherwise be unable to read the code. Comments are necessary in Praxis code. You will see single-line comments that begin with 2 forward slashes. You may also see situations where a question or direction may leave out a piece of code. In these instances, you may find a comment that looks like this line right here. This is also a comment in Praxis code and is typically nested within Praxis code. When you see this style of comment, the Praxis test is looking for you to choose the correct Praxis code to substitute in for the comment to complete the code. Python uses one statement to print output to the console. A Python print statement outputs its information and then moves on to a new line. This means that if we have 2 print statements, the output would print on 2 separate lines. Well-placed print statements can aid in debugging code as it becomes more complex. Print statements placed at strategic points in a piece of code can aid a programmer in identifying possible errors or incorrect logic. When creating output in Praxis code, we'll begin with printing. In Praxis code, the statement that is used to print output is almost identical to our Python print statements. print arg. As you can see from the statement above, Praxis code does not require any symbols at the end of the statement or within the print statement to output a value to the console. Each print statement will output on its own line unless otherwise noted. So you can print 5, will print the number 5, print, quote, hello world, will print hello world, and print 5 plus 2 will print 7. So these statements will result in the following printed to the console. Python is a dynamically typed programming language. That means that variables in Python are associated with the value that they have at runtime, and not any kind of named variable with a specific type prior to runtime. A dynamically typed language like Python allows for greater flexibility when calculating with and using variables. Variables are used in Python in similar ways as in mathematics. They hold values that can change and also need to be given a name. Unlike math and Python, Praxis code variable declarations must have a type. In other words, they cannot just hold any value. Their type will determine what kinds of values the variable is allowed to store. The int data type can store a positive or negative integer value from negative 2,147,483,648 to positive 2,147,483,647, or 4 bytes of storage. Here are some numbers that can be stored as type int. 35, this number here, negative 46,573. Integers are positive or negative whole numbers. 3 is an integer, but 3.2 is not. Negative 57 is an integer, while the square root of 2 is not. If the value of the number is larger than this number, 2 to the 31st power minus 1, or less than negative 2 to the 31st power, then the computer will cut off all excess digits as if they were not there. Once a numeric value surpasses the maximum length for int, it must be stored as a different type of data. The data type int is for positive and negative integers. When you need variables to hold decimal values, we use a different set of data types called floating points. There are 2 types based on the decimal point accuracy. Float has about 7 digits of accuracy, 4 bytes of storage each. Double is about 15 digits of accuracy, 8 bytes of storage each. If you type in a number with a decimal, it is considered to be of type double, even though there is no variable. For the Praxis exam, we will use the term floating point when referring to decimal values stored in variables. Boolean data types can only have a value of true or false. Here are the possible values of a Boolean. In Python, they must be capitalized, true and false. These data types will prove more useful later when we review loops. They're good for storing the answers to yes or no questions. Char, or Char, is used for computers to store any single numeric or non-numeric character. That includes anything on your keyboard: lowercase letters, capitalized letters, numbers, spaces, slashes, enter, space, tab, etc. The single character is placed between apostrophes. For instance, apostrophe T apostrophe would represent lowercase t. All of the Python data types we've just reviewed are used on the Praxis exam. The characteristics of each of the types remain the same when they're being used in Praxis code. So here we have int, float, boolean in Char. We have those same types in Praxis code. Variable names start with a letter or underscore. There's no practical limit to the length of variables. Variable names are as long or as clear as needed to explain what the program is doing. The correct syntax in Python for assigning data to a variable is by using an equal sign, shown here. The variable name equals the data. So if we want to declare a variable that holds an age, you could write age equals 30. The variable name is age and the data value is 30. Although it isn't specified, since age is holding the value 30, it is understood by Python that 30 is an integer value. Variables in Praxis code look slightly different than they do in Python. The type is needed in addition to the variable name and the data. The assignment symbols also differ. So here we have type, variable name, then an arrow, and the data. So declaring a variable that holds a person weight would look like the following. Float, because that's the data type, weight is the variable name, and then we're going to save the value 101.5 into that variable. That's why there's an arrow pointing from the data to the variable name. Here are some more examples. Char, first letter, is B. Double numpy is 3.14, etc. Boolean, am I very smart, is set to true. Int, we are using a very long name for this variable, is 4. Variables must be created with a value stored in them, unless they are a parameter. We will discuss parameters in the future. Variable names cannot have any of the following characteristics. They cannot start with a digit, contain punctuation, be a keyword or reserved word used by Python, or contain spaces. So all of the following variable statements are illegal. Int 3a starts with a digit. Int dove's variable has an apostrophe in it. Long is a keyword used by Python, so it cannot be a variable name. Same with while. And here we have a variable name that's using spaces, so that is also illegal. You can change the value of a variable as many times as you want, and it can be used in a print statement to output it to a console. Remember, only use the data type once when you create the variable, not every time you change the value. So here we're declaring what is my value variable, and we're printing the value that is being held by that variable, which is currently 1. Then this line here is changing the value to 2. So now when we print whatever's being held by this variable, it'll print out a 2. Then we have what is my value is set to 3, so this statement here will print 3. And you can see we only use int, the data type, in the beginning. So to go over this one more time, even though we have the exact same print statement 3 times, each time it is run, a different number is printed out. First a 1 is printed, then a 2, and finally a 3. This is why variables are so useful in computer programming. Computers use very similar operators to perform arithmetic operations on numeric values as mathematics does. Operators, such as those shown here, can be used to add, subtract, multiply, divide, and find the remainder of a division operation. The standard math operators for Python and Praxis code are addition, subtraction, multiplication, and division. To do each, we use the plus sign, the minus sign, the forward slash, and the asterisk. In addition to the previous 4, we can also calculate the modulus, or remainder, for which we use the percentage sign. If you set a variable equal to the modulus of 2 numbers, it will provide the remainder from the division operation in integer form. See the examples below. So here, int x is going to be set equal to 11 modulus 3. 3 goes into 11 3 times with a remainder of 2. So 2 is going to be assigned into x. Here, 14 modulus 5, 5 goes into 14 2 times evenly with a remainder of 4, so y will have a value of 4. Modulus is asking what is the remainder after performing long division with 2 numbers. In the first example above, 11 divided by 3 would have a remainder of 2, which is why the x is 2. When working with arithmetic operators, order of operations from mathematics still applies. Parentheses can be added to any arithmetic expression to prioritize which expressions within an equation should be evaluated first. Remember PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction. So parentheses take top precedence. The assignment operator is the lowest precedence. The modulus operator, in terms of level of importance, is ranked with the multiplication and division operators. If there are several operators of the same precedence, you work from left to right. Let's look at an example. What is the value of x after the following statement is executed? Alright, so first we begin with 8 minus 3 becomes 5. Then we start at the left, we do the modulus first, that gives us a remainder of 2. Then we do the multiplication, that gives us a 10 here. Then we do this division, which gives us a 2, and 2 plus 2 is 4. And it's saved as 4 because it is an int. Int x is 4. Whenever Praxis code has a smaller, less capable type, it can automatically convert it to a more capable type. This can happen in 2 situations, one of which is assignment promotion. An int can only hold whole numbers, while float has a fractional portion. If you assign an int to a float, a 0.0 will be added temporarily to the number for the assignment. Note how this does not change the value. Here is an example. Int x is 1, float y is x, so whatever is currently held by x will be assigned into y, but this is a float, so now if we print y, we see that that 1 has been upgraded to a 1.0. When working with variables in Praxis code arithmetic expressions, pay close attention to the variable type, as you may need to cast. The code above will cause a compiler error, since we're trying to assign a float value to an int variable. How can we use type casting to fix the problem? By adding int in parentheses to the front of the operation, we are telling the computer to do the calculation and then save it as an int. Remember to put the operation in parentheses. The output would look like this. In Python and Praxis code, the type that holds a sequence of characters, like letters, numbers, or symbols, is called a string. A string is not a primitive data type like int or char. It is a class, and we will be learning about classes later on. Unlike char, which can only hold one character, a string can hold many characters. Earlier, when we made our computer print out "Hello World," we were using a string. A string literal is the value that is assigned to a string. In the example below, "Hello World" is the string literal that is assigned to the variable s. Praxis code uses the string class to allow for the storage of multiple characters in one place. This means that strings in Praxis code can also hold words or phrases like they can in Python. Similarly to how primitive type variables are stored, strings use an arrow to assign data to a string and include double quotation marks around the string literal. So here we have the type string and we have the arrow instead of the equal sign for Praxis code. Let's take a look at the new program. We know we're dealing with Praxis code here because we have class hello world and then end class hello world. And then here, instead of just printing hello world, now we're going to save hello world into the variable s and then print that variable. And that will print hello world. The plus sign is not just for adding numbers. It can be used for string concatenation, adding multiple strings together to make a longer string. So we're saving 2 string literals added together, ABC plus DEF. Printing out that variable gives us ABCDEF. Pay close attention to spacing when combining string outputs and variables. If you're printing out a string, be sure to provide the correct spacing. Otherwise, the example below shows how the output will look. If we have 3 strings, 1, 2, and 3, the first one says programming, the second one is, the third one is fun, and then you print 1 plus 2 plus 3, it will print all 3 of these strings in a row, but there won't be any spaces between the words. A string's content is not one value, like with types such as int, boolean, float, or char. Each character within a string is identifiable. In other words, if we have the string day set equal to the string literal Monday, we can write a program to recognize that the 4th character in the string is a D. Each place in a string has what is called an index value. Consider string greeting below. String greeting is hi there. The index values for each character are listed here. 0 for H, 1 for I. The space has an index value of 2. The T has an index value of 3, and so on. They start counting at 0. and continue through the length of the string, including all spaces and characters. So H is index 0, the space is index 2, R is index 6, etc. Index values can be used by procedures to access and retrieve pieces of a string and store and use them. There are a few procedures that are very useful when working with strings. We have to lowercase, which converts the characters in the string to lowercase and then returns the string. To uppercase converts the characters in the string to uppercase. Substring returns the substring of the string from one position to another position. So it can get you just a few characters from the middle of a string, for example. And int length returns the length of a string. The length procedure determines the number of characters in the string and returns an int value. For example, if string B is race car, and then int L is b.length, it will take the length of string B and then save that into the L variable as an integer and then print that number. So this will output 7 to the console. So notice that for this string, the last index would have a value of 6, but its length is 7. Since the index starts at location 0, the length will always be 1 more than the ending character's index value. The substring procedure is able to take a portion of a string and return that subsection of the original string. For example, if string B is race car, string N is going to be a substring from string B from 0 to 3. Now, it's going to include the character at index value 0, but it will not include the character at index value 3. It will stop at 2. So this will be index value 0, 1, and 2 from this string here, giving us RAC. Here we have string M is the substring from B, of race car, from 5 to b.length minus 1. So it's going to start at index value 5, which is this A right here. Then it's going to go to b.length, which is 7, minus 1. So this whole portion here is 6. Therefore, since it doesn't include the character at index value 6, it will just be that A. So when the substring first, last, minus 1 procedure is used, it takes index information. The substring begins at the first index listed here, inside of the parentheses, and ends at the index that is 1 less than the second index listed. The to uppercase and to lowercase procedures perform the functions that they're named after. To uppercase will make all of the characters in a string capitalized, while to lowercase makes every character lowercase. For example, if we begin with string B is race car, and then we want to save to uppercase version of string B into string A, that will save race car in all caps. To lowercase will save it as it currently is, all lowercase. No programmer is expected to write code that doesn't have any mistakes. That would be unreasonable. However, programmers are expected to be able to use their IDE or editors to help them quickly find and correct errors. We'll review a few types of errors before getting into more involved programs, such as syntax, logic, compile time, round off, overflow, and runtime errors that can occur in programming. We'll use the example Python code below as a reference. A syntax error is caused when code is missing a critical symbol, a letter case, or piece of information that would prevent the code from executing. This can sometimes be referred to as a compile time error, as a compiler can catch missing syntax. So here, we see an example of a syntax error on the circled line of code. At the end of the statement, there should be a colon to end the line of code. A logic error results in an error on the user's part when they fail to consider a scenario, or they use incorrect ordering of the code that causes a bug in the program where the correct result will not output, but the program will still execute. So here we have a program, class finding errors, Fahrenheit is set to 27, Celsius is set to Fahrenheit minus 32 times 5 divided by 9, then print Celsius. So we're going to want to convert from Fahrenheit to Celsius. However, The formula that is used to calculate the temperature in Celsius is correct except for one thing. The logic error is created because the parentheses surround 5 divided by 9, when really there should be a parentheses around Fahrenheit minus 32. So this will print an incorrect number. A runtime error occurs after a program compiles and attempts to execute. Although the program does not contain any syntax errors, during runtime, if it asks the computer to do something that it is not capable of doing, a runtime error will occur. So here we have my age equals 27, num equals 0, print my age divided by num. Even though there aren't any syntax errors, dividing by 0 is a calculation that is impossible for the computer or anyone to evaluate. This results in a runtime error. An overflow error is an error that occurs when a program attempts to store too much information in the wrong type of variable. An example of this would be attempting to store a value that is longer than 2 to the 32nd power minus 1 in an integer data type. A round-off error occurs when a number has been rounded and then used in a calculation, and it provides a smaller and incorrect result. This sometimes occurs when the mathematical value pi is rounded and then used repeatedly in calculations that may result in an incorrect answer. We'll now use the data types we've discussed, like integers, floats, characters, booleans, and strings, in more advanced programs. As we navigate more complex algorithms, we can be guided by these 3 types of control structures. Sequence, which is a series of precise statements. Selection is where the algorithm can select one of multiple paths. And repetition, or iteration, where the algorithm can repeat a sequence. These are the basic building blocks of algorithms. We will begin to use flowcharts to help us understand these control structures and also to draft our programs. The code below has a sequence. How could you represent this sequence in a flowchart? Did you get something like this? It's okay if you used all rectangles, but do you notice the parallelograms in this solution? Flowcharts use different shapes to represent different but universal meanings. The parallelograms represent input and output. So here we start, we set A equal to 1, we print A, then we set A equal to 2, we print A again, then we set A equal to 3 and print A a third time. This program is an example of sequence. Each statement directly follows the previous statement, and the computer executes each statement in order.